Hello, good morning to everyone. As the president of the Italian Association for Artificial Intelligence, I'm really proud. It's a real pleasure for me to announce the starting of the autumn program on the Spotlight Seminars on the AI. After the great success of the spring edition, we are now back with free seminars, and in particular, I announce to you that on December, we will have Francesca Rossi from IBM Watson Research Center. On January, we will have Alfonso Gerardini from University of Brescia. And today, it's a great pleasure to have with us Roberto Navigli from Sapienza University of Rome. As you probably know, Roberto is a very well-known researcher in the area of natural language processing. And with this respect, we started a collaboration. We are also very proud to have these joint activities with the Italian Association for Computational Linguistics, which is an association which is very active in the field, in the specific field of artificial intelligence. It promotes and disseminates methodological, theoretical, and experimental activities, scientific collaboration, development of shared practices, resources, and tools. And so today, we thought that the best way to introduce Roberto Navigli is actually to give the opportunity to present Roberto to our trade union between the Italian Association for AI and the Italian Association for Computational Linguistics. And this trade union is Roberto Basili, who is a well-known member of the community of computational linguistics, but is also a member of the board of Hyperion. So, Roberto, thank you very much for being here, and I would like that you introduce Roberto Navigli. And before that, Roberto, thank you very much, Roberto Navigli, for having accepted our invitation. It's a real pleasure to have you here today. So, please, Roberto.
Luigi, thank you very much. I understand that this area and the interesting research on which this talk is focused is very important because it's really the linguistic capability of intelligent systems are crucial to the notion of intelligence. So we all are very happy to be focusing on these topics. And the person, possibly the best person to give us a glance of the challenges that are behind this research, and also some directions. The best person is Roberto Navigli, that is an important member that gave contribution to the Italian community since mid-90s, and it's really a pleasure for me because Roberto has been able to promote research in several directions about natural language semantics, looking at the lexical semantics area as an area where resources, contributions, algorithms, so with a strong computational perspectives, were crucial to the notion of natural language understanding. That is, a really challenging question about understanding and knowledge, representation and usage in intelligent systems. Roberto has been able to join computational research with strongly principled linguistic research in the area of lexical semantics and sentence semantics. He has been receiving several awards that I am not here to list, but he was able to promote novel and original research in the area of word senses ambiguation, and through a couple of ERC projects, large-scale projects like MultiJedi and then Moose, he was investigating the role of lexical semantics and lexical semantic resource in the dimension of the multilingual treatment of semantic processing issues. This is in the middle, or is a crucial core notion at the crossroad of knowledge language, and also the application, because reasoning and decision making are strongly rooted on these notions. So Roberto was also able to give, with the large number of papers that in the international literature he was able to produce, and we all appreciated, novel research in the area of text processing from a semantic point of view. He was, through BabbleNet, the creator of large-scale multilingual resources that are useful for the communities. And this research has been also shedding some light, some important light, in application of these technologies to linguistic tasks that are so important in information retrieval, dialogue systems, and machine translation. It is an Italian excellence, and I'm quite happy to be here to introduce him. So I don't want to steal other spaces from him in this seminar, and I'm really happy to give him space and to invite him to start.
Thank you, Roberto, for the nice introduction. I want just to tell you that also Giuseppe De Giacomo and Marco Maratea joined us. They are part of the scientific committee which organizes these seminars, and they helped me a lot to define the program. And so we were very happy and anonymous, and we're very proud nowadays to have Roberto Navigli here. So please, Roberto.
Well, thanks a lot. I'm very honored to be here. Thanks for the invitation. Thanks, Iperia. Thanks, you all. I mean, it's really great to be here. And after this great introduction, I feel very excited, and also, I mean, I find it more difficult to give this introductory seminar because I'm a bit flattered and excited. So thanks a lot. So let me start. So the seminar, so I thought I would like to talk about a general area of NLP with a particular taste that is the one of neurosymbolic approaches to a key direction in NLP, which is natural language understanding with a specific focus on multilinguality. And I used some pictures and some a few slides from some of my students that you see here on this slide. I'm very thankful to them for this help, of course. And so in NLP, so if we have an NLP system, you can very simply say that there are two main directions in which you can work with text. Either a system takes text as input and performs some kind of understanding for this text and produces some representation of what was read in the text, or vice versa, starting from some data structure, representation, knowledge base, any type of structured or less structured information and knowledge that the system might have, generate some text and produce new text that, in a sense, either represents the starting information or follows from it. And so here we are focusing on the understanding side, even though a system could potentially include both sides of NLP. And in particular, I wanted to focus on semantics, which is my key area of expertise, and even more in particular, multilingual semantics. So by semantics, here I'm citing I'm giving three different quotes of texts and people who talk about what computational semantics is. But I think what is most interesting is that is to take some phrases here and there, and we talk about the process of constructing a reasoning with meaning representations of natural language expressions, which could be sentences, but could also be larger or shorter sequences of words. And we can also talk about formal semantics connected to computational linguistics and reasoning, because in an implicit or a direct way, we might want to reason about what we read or what we want to generate. And finally, I find it very interesting to say that we're talking about linguistic objects, which could be of different types, as I already said, like sentences, fragments, even dialogues. So there's quite a variety of elements that we need to consider when we talk about semantics and the meaning of these natural language expressions. When we talk about multilinguality, we mean we want to move from one language, which fortunately or unfortunately is more or less always the same, English, to tens, hundreds, and potentially thousands of languages. But when we talk about multilingual semantics, in a sense, we get the best of these two worlds with the idea of preserving the same semantic representation across languages. And so ideally, we would like to move from a surface form, from some text in a given language, to its underlying semantics, which potentially could be independent of the language. Like you see here, a sentence, and ideally, potentially, you could produce a representation that doesn't contain any of the words or very few of the words that are contained in the initial sentence. And so to give you my vision of multilingual semantics, what I see is multiple sentences, one the translation of the others, and obviously this is an easy case in which syntax is the same, but it doesn't need to be always the case, and in which the corresponding words or expressions are associated with the same concept, like for example here, cook, cuoco, cuisiner, or smell, or cake. They're associated with explicit concepts, and they are also organized into a more complex structure that relates the various concepts across the sentence and also across languages in a way that is ideally independent of the language. And so we'll go through this journey, obviously in 40 minutes, more or less, of what is around currently in terms of research that aims at producing this kind of representation. But the first question that a colleague of mine, or even someone who has been reading papers in NLP recently, that would arise is, why would you really want to do that? Because actually, we have all seen big success of deep learning approaches in many different tasks in NLP, especially with the advent of pre-trained neural language models like BERT, GPT, BART, all of these models that are currently used to perform NLP tasks. And many of the different tasks, like ranging from autocorrection to machine translation, we have seen huge improvements in performances, not to mention virtual assistants, market intelligence, question answering, text summarization, sentiment analysis, and many other tasks. So why do we really feel, or at least I feel, the need of going beyond what deep learning can do? That is, process text, produce an output, or produce text starting from an input, without necessarily making explicit the understanding of what has been read or what is going to be produced. Well, there are a number of reasons. Deeper semantics, I believe, is clearly needed for the next generation of intelligent applications. And there are many reasons. One is interpretability. So I can interpret what was understood by the machine, and I can maybe modify it by manipulating it, and later re-inject this information in order to improve the quality of the NLP system. I can also work towards accountability. So maybe the system will be able to explain why some approach is, some output is produced. And it will also be more scalable towards many languages, because it's true that language models can work with multiple languages at the same time, but we also know that the performances are not the same. And so scaling, being able to scale multilingually, is something that is enabled by explicit semantics. And finally, generalization power. So if I associate a concept with a word, then I can leverage this concept to generalize. And so if we look at some example, and I can find tons of these examples, obviously we know that machine translation now works much better than some years ago. However, it doesn't seem to understand, especially when a word is used in a non-predominant meaning. Like, for example, here I say, I stood by the bank looking at the ships, and I get stavo vicino alla banca, which is the financial institution, guardando le navi. The rest is fine, but banca is wrong. And so even if I give more context and I say I was taking my usual walk down the river, however, this time I stood by the bank, it still doesn't get it. So there must be something at the root, at the core of these systems that doesn't really aim at understanding, at using semantics, common sense, and all the type of information that we humans use that allows us to avoid these kinds of mistakes. And if we read this interesting paper from 2 years ago by Bender and Kohler, we see, in a sense, why this is the case. The point is that if we only look, so this is the octopus test. Unfortunately, we don't have time to introduce properly, but the main idea is that if an octopus can intercept a communication between A and B without having any knowledge of the word, without having any common sense information, without really being able to associate semantics with the form, with the sequence of tokens, the sequence of words that is actually exchanged between A and B, the octopus is only reasoning and working on a sequence of symbols that don't have any explicit meaning or knowledge of the word attached to them. And so in cases when we need that kind of knowledge, the octopus, by intercepting the communication and replacing B, wouldn't be able to answer relatively simple questions like, there's a bear, all I have is a stick, what do I do? And the answer is, the bear is chasing me. Or, I don't know, take the stick and put it on your head. You know, these things don't make any sense, but to a language model, they do. And so this is where we are working. I mean, this is where we would like explicit semantics to help and to justify the choices made by a neural model. And this is where we're heading. So we say neurosymbolic exactly because we believe both in neural approaches, but also in modeling the knowledge in a more explicit way. And so the seminar is organized to very briefly introduce 3 core tasks that aim at making human intelligible multilingual natural language understanding. There are 3 tasks: word sense disambiguation, semantic role labeling, and semantic parsing. Obviously, I will have to devote no more than 7-10 minutes to each of these tasks, so I'll be brief and focus on the key elements of each of them. And so, starting from word sense disambiguation, we are now in the area of lexical semantics, so semantics of words. So we are focusing on the individual meaning of a word in context. And so we can define WSD as the ability to identify the meaning of words in context in a computational manner. For example, if we take a sentence like a mouse takes much more space than a trackball, and we focus on the word mouse, we can have this word can denote multiple meanings, like the rodent meaning, the device meaning, or even a person who's quiet or timid. But actually, in this context, we are interested in the hand-operated device. And why? How do we understand this? Well, thanks to the context, but also thanks to the ability for a system to know the possible meanings that this word can assume. And so, and for this, we need a resource, one or more resources that is able to list the various meanings of this word. And in this case, we're using WordNet, which is a very well-known resource that I'm going to introduce. And so WordNet is the most popular dictionary and computational lexicon of English. It has a very interesting organization because it's not just a dictionary like many others that we see online or that we used on paper. But it's also organized as a graph of concepts, and these concepts are mapped, are one-to-one with so-called sets of synonyms. And so in one concept in the graph, I have all the synonyms that are used in a given language, in English in this case, to express that specific concept. So car, automobile, motor car, and so on. And a word sense, so a sense of a word, is just a word occurring in such a set of synonyms. And so a word here would be a sense among the various synonyms that are used to express that concept. But if the word is ambiguous, it will occur in some other node in a different meaning. Okay. And so synsets are also associated with textual definitions that are called glosses. So these are the traditional definitions that we find in a monolingual dictionary, for example. A motor vehicle with 4 wheels as a definition of car. Not only that, but also the edges are labeled via using a set of predefined lexical semantic relations. And these are generalizations like hypernymy relations, also the inverse relation hyponymy, like, I don't know, hypernymy, a bunk bed is a bed. Also meronymy, part of relation, like a chair as part of the leg. Troponymy, which is the equivalent of hyponymy for verbs. So talking is a way of communicating. Entailment, snoring entails sleeping. And many other relations that make up a graph of almost 120,000 nodes. The positives of WordNet are that we have an interesting intersection between a standard electronic dictionary and a thesaurus, because the synset implements some kind of thesaurus encoding, while the structure and the other information implement the dictionary side of it. Plus, we have, in a sense, a lexical semantic knowledge graph. And we have wide coverage. So we can safely say that most of the content in WordNet covers the widest part of large part of the English language. However, there are also limits. This project was started by George Miller for the English language. Later, we have seen some other WordNets in other languages, but at smaller scale. And so the limit is that these resources are monolingual, and most of the time that they contain general dictionary content only, which is, in a sense, lexicographic information. So they don't contain most of the encyclopedic information that we might find in resources like Wikipedia. And this is why now 12 years ago, we started to work on a project called BabbleNet that aimed at bringing many different resources together in order to create a larger resource that would increase coverage, enable multilinguality, and bring together lexicographic information that we would normally find in a dictionary like WordNet with encyclopedic data, encyclopedic knowledge that we normally find in resources like Wikipedia and later Wikidata. And later we started to integrate more resources like Wiktionary, which is also an electronic dictionary, and many others. And so BabbleNet is a growing project with more and more resources being integrated and continuously updated. The key idea of BabbleNet is to extend the synset model multilingually. So to say, it's not just a set of synonyms in the English language or in a given language. It's the set of lexicalizations, it's a set of synonyms of terms that are used across languages to express that concept. And so, for example, extending the English synset, we also have macchina, autovettura, voiture, and all the other words and the other languages are used to express the meaning of car. And this is thanks to the algorithmic integration of these resources, because once I link a given WordNet synset to a given page in Wikipedia for the corresponding concept of car, then I can bring together all the other counterparts written in the other languages that define the same concept in the other languages, and take all these translations together, their definitions, their pictures, and so on, and create a single synset as a result of the integration of all these pages and entries. And currently, BabbleNet covers 500 languages, contains 20 million synsets, and more than 1 billion lexicalizations, and much, much more. Now, how do we use these resources, WordNet, BabbleNet, potentially any other lexical semantic resource, to perform the task of word sense disambiguation. I'll give a simple example that is, however, quite recent because it's based on BERT as a transformer-based model. And so we give as input a sentence and we're interested in a given word in the sentence. This goes through the BERT embedder, and it's encoded, and then it goes through a feed-forward neural network that produces at the output layer a probability distribution over all the senses that are available, for example, in WordNet. Then, of course, we have to apply softmax because we want to obtain to give higher importance to those meanings that are highest probability, have high probability, and we also select only those meanings that pertain to the target word. And so we focusing only on those meanings, we can then choose the highest probability one. And so in this case, for example, the suit meaning, the correct one, is the one that is related to cards. And so, in a sense, besides the deep learning part, this is as simple as training with the right data a neural model in order to choose the most likely meaning for a given word. Interestingly, these models enable the possibility of moving from one language to another. For example, if I use a multilingual model like XLMR, I can train the system only in English, and maybe that's because I only have English training data with annotated with the right senses in WordNet, and then input Italian sentences or sentences in any other language, and still produce a probability distribution over the same inventory that, for example, could still be the WordNet inventory. Now, what is the point of doing this? It's an English inventory, we said. However, WordNet is part of BabelNet. And so this means that if I produce as output this meaning, I can see whether Seme is part of the corresponding scene set and use it as a potential candidate for the output of the same system. And so thanks to a multilingual resource like BabelNet, I can choose, I can focus on a given language and select only those senses that are of interest to that target language. And so this is already a relatively simple result, but it makes it possible to train only in a given language and then perform word sense disambiguation in potentially any language. The results of such a simple approach are interesting. For example, if we compare the previous systems like green and blue bars here that are graph-based, more or less, with this relatively simple neural approach, we see that overall we get some improvement, not an exciting improvement, some improvement. We also see that performances are not that great, like 74 means that 1 out of 4 meanings are not correctly identified, which is not that great. But when I was doing my PhD, it was 62, 63%, so it was much even worse. However, there are many more ideas to increase the performances of such systems. And one of these is to use a neurosymbolic approach. What does it mean? It means that we leverage the information that is available in the graph, for example, in the WordNet graph that I just introduced, to improve the ability of the neural model to choose the right sense. And we can do this within the set of matrices that make up the neural model. For example, by combining the logits of not only of the related senses to one of the candidates under consideration. For example, in the suit sentence that we had before, these are 2 possible senses of the word suit. So one is the cloth, one is the card meaning. We not only do we consider the logits of these 2 meanings, but we also bring together, we also sum the logits of related meanings. thanks to the WordNet graph. And as a result of summing this information within the matrix computation, we bring together, we increase the probability of the potentially of the right meaning compared to potentially decreasing the probability of other meanings that are not, whose logits are normally lower, and also the related senses should also have lower logits, and so overall a lower probability. And so as a result of this, we expect higher performances. But we also have another way of applying a similar idea. So we still use the WordNet graph, but rather than doing this at test time, so when we have a sentence and we have to decide which sentence to choose for suit, and we aggregate the logits of the candidate with its related sentences, we can also do this at training time only. So we say in the label of in the loss of the neural network, what we say is, for us, it's good not only to output one of the candidates, but also to choose as a good candidate related sentences. And so by giving high probability to related sentences, in a sense, is equivalent or goes in the direction of reducing the loss if the candidate is the correct meaning, or it increases the loss if I give high probability also to related sentences of the wrong sense candidate. And the advantage of this is that we don't have to take into consideration this information at test time. So we just train the model to do this. And in both cases, what happens is that if I apply these two approaches, which are these two bars here, compared to the standard fully supervised approach, we get an improvement of 4 to 5 points, more or less. And so this is very interesting, because it means that the neurosymbolic approach that exploits both knowledge and training data can improve the ability of a system to understand the meaning of a word in context. There are also more recent approaches that take us to 82%. Now, we don't have time to discuss them. It's interesting that, however, that we are still at 82%. There are reasons for this, but we don't have time to discuss them. So if there are questions later, I'm very happy to answer them. This system is actually implemented and is online, and so everybody can use it. And you just go to this URL, and it's called Amuse WSD, and it works in virtually any language. So you give as input a sentence, and you get as output an association of BabelNet synsets that you can click on, and then you can retrieve the information from BabelNet and see, potentially translate this in another language if you want to see what Quick or Brown or Fox in this particular context means. And now we move on to the second task, semantic role labeling. And so we are now in the area of sentence level semantics, where the interest is not only focused on a single word, but on the predicate argument relations. And so what does it mean? Semantic role labeling can be defined traditionally as the task of addressing the questions who did what to whom, where, when, and how. And if we take our sentence example, the quick brown fox jumps over the lazy dog, we have to perform 4 main tasks. One is predicate identification. So we have to identify those words that, in a sense, drive the meaning of the sentence or part of the sentence, like, for example, jumps here. Then we have to disambiguate this predicate by associating the most appropriate sense for that predicate. Then we have to identify for that predicate sense the arguments. And so, for example, here we have 2 arguments, the quick brown fox and over the lazy dog. And finally, we have to classify the arguments. The first one is who, and the second one is over what. So there are 4 tasks. In many cases, we focus on the argument part, so the assignment of a semantic role to a given predicate argument pair. This is the key part of SRL, but potentially you should be able to perform all of the 4 tasks. And now we don't have time to go into the details of this task, But I think the most interesting and related to what I already mentioned earlier part of SRL is how to perform this task across languages. And so now I'll show an architecture so that we'll see how to perform the task, but we'll also keep in mind that there are issues. And the issues are that if you think about the predicate disambiguation task, this means I need an inventory for each language and for each and every word in that language. And what is this inventory? You might believe that the inventory is probably WordNet, or if we move multilingually, BabbleNet. Actually, this is not the case. Historically, there are other resources that have been created for semantic role labeling that are normally coarser grained, so they have a coarser granularity, so less meanings for a given verb. Verbs are very ambiguous most of the time. And so for English, the resource of the reference resource is the English prop bank, which is quite a large inventory of verbal meanings, verbal predicates. And there are other resources also in other languages with different coverage. And unfortunately, we don't have such resources for all languages, which in a sense recreates the issue of how these resources talk to each other, whether they talk to each other, and how heterogeneous they are, and whether then I can scale to more languages. And so this is the challenge I wanted to focus on today. And the point is that multilingual, cross-lingual approaches have this issue that either you stick to using a single inventory. So you say, I will use the English prop bank for all languages, which is already kind of weird, because what does it mean that you have, I don't know, eseguire disambiguated with run 01 or 02? I mean, this is really a bit weird. Even though this is one of the most popular approaches. And the way to do this is through parallel corpora or projecting annotations from one language onto another. So, for example, I take a training data set in English, annotated with English prop bank, and I project the run 01 annotation to the corresponding word in the Italian translation eseguire. And then I train the system in Italian with the English label. This is an idea. However, in my group, we had an intuition that maybe we could learn from multiple heterogeneous linguistic resources by leveraging multilingual language models and multiple heterogeneous resources in different languages, so that we use multiple sets of meanings in different languages and take advantage of each of them in order to learn correlations between the different inventories. And so what we did was to create to put forward a neural model that takes as input a sentence and produces word representations for each of the words in the sentence, and then uses a so-called universal sentence encoder to produce an output for predicates and for roles, so for the verbs and the corresponding arguments, in all the various resources that are the various inventories that are available in different languages. Of course, when I train it, I give as input a sentence in a given language, and I train it to produce the right output in the corresponding language. For example, if this is Spanish, I'm going to produce an output with Ancora, which is the relevant inventory in Spanish. But then I also take as input an English sentence, and I train it to produce the right output with the English inventory, and so on. If I do this at once with multiple languages, then what comes out is that both on the predicate and role sides, the system learns to produce the right output for the corresponding language, but also the corresponding thanks to the sentence, the universal sentence encoder, the corresponding meaning in the other inventories and other languages, including a multilingual inventory that we created called Verb Atlas. And so now I'm not going into the details, the scary details of the deep learning part, especially for the sake of time. But the idea is that, as you see here, you have one output sense for each inventory, for predicates and one output role for each inventory of arguments. And so, and we leverage the predicate information to make a choice for each word and decide whether and how to label each word with the corresponding role. If we look at the performances of such an approach, what we did was to pretend we don't have the full amount of data, because that's the standard case in languages where we want to scale. So if we want to work with Italian, which has virtually no data for semantic role labeling, the idea is what happens if I train it on 10% of the current available data, which is relatively small amount of data, monolingually, or if I bring everything together, so I leverage all this information across languages. What happens is that performing this training across languages gives a boost in all languages, with some languages having a considerable increase in performance, like, for example, Spanish and Catalan. But also in other languages, we get improvements of 6 points, or even in some cases even less. And so this is the quantitative result. But the interesting side is also that once I give as input a sentence, then I get as a result an annotation of predicates, like, for example, throw, across languages and across inventories, and also an annotation of the corresponding arguments using the different role inventories. And I can also take a sentence in a language that has never been seen before, thanks to the multilingual neural model, and annotate it with all these inventories, and including inventories that are multilingual by design, like Verbatas, which is based on BabelNet. And so as a result, I can basically perform semantic role labeling across languages. And I can also align these inventories. So, for example, I can associate criticize from Verbatlas with the Chinese prop bank predicate, the English prop bank predicate, and so on. And we're still working on this because it is quite a complex area. And there's, again, a demo that you can try out at nlp-1.it Invero. It's called Invero for Intelligible Verb Senses and Roles. And again, you can try it in multiple languages. And now we conclude the presentation with the third level, which is semantic parsing. Because now with semantic role labeling, we have connected the verb to its arguments, to its roles. But actually, in a sentence, you normally have an even more complex structure. Like here, when I say, you told me to wash the dog, actually, it's not only tell connected to you and I and wash, or wash connected to I and dog, but it's also their interrelationships. And so this is what we want to do with semantic parsing, to produce a graph representation of the input sentence. Actually, I can do both text to graph, and we use here what is called the abstract meaning representation, which is a very popular graph representation of the meaning of an English sentence. So we can do text to AMR, abstract meaning representation, but we can also do vice versa, AMR to text. And this is the generation part. So I take a graph and I produce a text that is not necessarily always the same, but that expresses the meaning of the encoded sentence. An approach that is relatively easy to present in so little time is Spring, that we presented last year at AAAI, which is performs both tasks, both understanding and generation. But here I'm focusing on the understanding side, so text to AMR. And so the idea is relatively simple. If we can linearize the graph yeah, so here, sorry, there's a mistake, because actually sorry, it's correct. So if I can linearize the graph and I transform it into a sequence of nodes and edges that are represented as a string, basically, I want to compute the probability of the linearization given an input text. And so if I start with a pre-trained sequence-to-sequence model and I train it with linearized graphs in order to, I give as input the text and expect as output the seq-to-seq model to produce the hopefully right sequence, then I can perform. Then I have to reconstruct the graph starting from its linearization, and I'm able to perform semantic parsing. This is a neural approach that is quite popular and works very well also with these kinds of tasks, and better than other approaches that use a more graph-based approach. Obviously, we can also do vice versa, like AMR to text, by just computing the probability of the text given the linearization. As at the core of such an approach, we use BART, which is a pre-trained seq-to-seq model that leverages denoising to learn the right parameters that are able, given an input sequence, to reproduce the original sequence at the decoder level. And the interesting side, the key insight is that we can see AMR, the AMR graph that we want to produce as output, as a permuted or corrupted version of the English sentence. In a sense, the AMR graph also contains some English words, as you see here. So the nodes are labeled with the English words, and predicates are labeled with the verbs with some numbers that represent their meanings. And so, in a sense, the sequence that is given at that should be produced at decoding level, it can be seen as a corrupted version of the English input sentence. And so the vocabularies of AMR graphs and English vocabulary largely intersect. And so we train such a model with input sentences to produce a linearized version, and the graph can be linearized in multiple different ways using the Penman notation, or DFS or BFS of the graph. And then there's some post-processing to be performed, but very lightweight. The results show that, as I mentioned earlier, that compared to previous approaches that tend to use more complex ideas that work more on the graph, or more at the level of some of the tasks, like only producing the sequence of nodes, or only producing the sequence of edges, and so on, using this linearization plus seq-to-seq neural model, so that brings together the knowledge graph with the neural approach, provides a big boost in performance. This number is hard to explain, because it's based on a measure called BLE that computes that compares the output with the gold standard expected output. So it's very hard to get close to 100 here. Again, there's a demo, so you can see you can try any sentence for this demo only in English to produce a Penman version of the graph that then you can also view visually. And finally, recently this year at AAAI, but also at ACL, we presented an idea that is the final part of the second ERC grant that is about to finish, in which we move from an AMR graph, where, as I said, there are words as nodes, to a conceptual graph where the nodes are not connected to the original language. So you only have concepts from BabelNet and predicates from Verbatlas, and so there's virtually no word from the original language. So we produce a fully semantic representation. This is the dream. We still have very interesting results, but there's still some work to be concluded. The interesting side of having such a representation is that sentences written in different languages that express the same meaning should ideally have the very same graph as output. So to conclude, I gave a brief introduction to three key tasks in multilingual natural language understanding, word sentence ambiguation at the lexical level, while at the sentence level we talked about semantic role labeling and semantic parsing. These tasks, even though there's quite a lot of research to be carried out, are quite mature compared to 10, 15 years ago, as you can see from the demos. There are still several issues, including the paucity of data in non-English languages, setting a level playing field across languages, and working with software notions of meaning, like you might want to make these distinctions fuzzier or working better for a given task. And there's much more to say in this direction. So this is all, and I thank you again for the invitation, and I hope there are interesting questions to answer.
Thank you very much, Roberto. It was a very, very nice talk. It was really a pleasure to see this great picture of what is relevant today in natural language understanding. I would like to invite everyone who is attending online to write down the question directly on the chat. We have a few questions. Then I also recall that the streaming will be also recorded and will be available on our YouTube channels also later. So for those who cannot attend nowadays in streaming, I would like to start the discussion with a general question related to the fact that you mentioned a number of times the graph-based methods, and then you contrast them with deep learning methods. So do you see, so what's your feeling about the power of graph-based compared to the power of deep learning-based? So some general intuition, and when one should choose one approach and when should choose the other approach?
Yeah, so I've been actually working on graph methods for many years, and during my PhD, my approach to WSD was graph-based. Today, if you want to be at a level that is the state of the art, you certainly need a neural approach, because, I mean, at least if you have enough training data. And so my view is that currently using knowledge-based approaches, which are the ones that use graphs, is not the best way to go. But the idea would be to integrate this graph information into neural models. So just using graphs doesn't take you to the same level of performance. So I don't recommend that today.
Okay, thank you. Thank you, Robert. So I think that this mixing a symbolic and a sub-symbolic approach is also your ideal choice for the future. So we have
the state of the art. Otherwise, there are interesting results also only from graph-based methods.
So we have a question that was posed during the first pass. So there is Marco Manna, who was asking about the charts of the sample given during the first task, the quality of the approach, so the bar ranged between 16 and 82. So are these percentages? And if so, how to establish whether 100% is reached? So this is a question related to how these performances are in general measured. So how these metrics are computed.
Yeah, so this is F1 performance. Normally I have it on the y-axis, but here it disappeared. So F1 is a harmonic mean of precision and recall. So this is most of the time these systems are always given an answer. So this actually corresponds to both precision and recall, and this means that we can safely say that these systems are answering 60, 70, 80% of the time correctly or not. What does it mean correctly? Actually, this would, require quite a long discussion. We don't have time to start. Unfortunately, the inventory that we are using, WordNet or BabelNet, is quite fine-grained. So that sometimes you give as output a sense that is incorrect for the annotators, but it actually is very, very close. Like there are two meanings of streets, including or excluding sidewalks. Do you really want to distinguish between them? And so in this respect, this is why when I said we are now at 82, this doesn't mean that we are doing so bad. Actually, the remaining 18%, is probably part of it is just choosing a sense that is very similar or very close to the right one. And actually, this takes us to work that I couldn't present, that is a work that actually aims at using definitions rather than predefined senses. So textual definitions and choosing between possible textual definitions as the best possible sense, which opens the way to new inventories or new definitions and so on. But there's no time, unfortunately, to present this. You can find it in this paper, Barba et al. That's an idea.
Thank you. So let's go to another question. So this is also very interesting. Carlo Adornetto is asking, in many sub-areas of AI, we hear about ethical issues. So what are the main risks when it comes to NLP?
Well, quite a few. If we consider, for example, the problem of well, first, all these pre-trained language models use data that is online, but whose license is unclear, because and that's why in many cases the text data that is used to train these systems on is not downloadable as a data set. You have to recreate it yourself at your own risk. And there's also an issue of a serious like a serious issue with all types of biases. So systems are biased, and using data to then provide answers to user that wouldn't like a certain bias towards any kind of discrimination, any kind of treatment, any kind of use of text, and so on. This would also create problems. And so, not to mention the ethical level, every time you have to create data sets, the way you create this data. And so, are you using expert annotators that you pay enough? Are you using crowdsourcing? And this creates all kinds of issues. So this would take forever to discuss. So I think there are a lot of these kinds of issues that are between ethics and social acceptability of the text that is produced, and how it was produced, from where it comes from, and so on.
Okay, thank you, Roberto. Then meanwhile, I ask to Marco and Giuseppe if they have questions, but we have another question for the moment from YouTube. Marco is asking about BabbleNet. Does the English version collect all semantic relation acquired from pages in other languages?
Yes, it does. So because in here, I guess we are talking about, there are different resources that are integrated. So, for example, if we consider Wikipedia or Wikidata, let's focus on Wikipedia. If I take Wikipedia, we link the English page, hopefully the right English page of a given concept, to the corresponding English WordNet scene set. And then, as a result of this linking, we take all the information also from the other pages, as I said, like Automobile, Voiture, and so on, in the other editions of Wikipedia. Then the hyperlinks that are available in the various Wikipedia pages are added to the BabbleNet graph. And so the connections that you find within the the English car page, for example, car is connected to Ferrari. Then you also get this edge within the BabbleNet graph. And these edges are, in a sense, supported by the number of times they are mentioned, they are included as hyperlinks in the various editions of Wikipedia. But for example, for Wikidata, you have typed labeled edges that come because it's a formal structured knowledge base. And those relations are typed and they are just taken and included in BabbleNet.
Okay, thank you. So, Giuseppe or Marco, do you have any question for Roberto?
I do have a question. But can these technologies be used for ancient language? So for some sort of archaeological studies, or so languages that we don't have much about. So we are full of holes, and somehow we need to fill these holes, maybe with other language, or with somehow getting the sense out of our more general sense of what a natural language is.
So the explicit technologies, because they require an existing inventory or existing information about that language, wouldn't be directly applicable. Because unless you have, for Latin or Sanskrit, you have, of course, but if you want to decrypt some language that you cannot understand, then you couldn't do this. However, you could use word sense induction techniques, like identifying the meanings of words by inducing them. there are such techniques, but this takes us to the clustering issue. That is a hard one, and there's no gold standard, so it's hard to evaluate. So all kinds of issues, you run into all kinds of issues. Or you just use other approaches that are less explicit and more latent, just using taking advantage of other techniques that don't use pre-existing inventories, because of course in this case, even though we cover hundreds of languages, of course if you then focus on linear B, you don't get any connection to it. So you definitely need to use other approaches to that.
Thank you. So Marco, do you have some questions?
Yes, just very quick, because we are 1 minute late already. Roberto, I'm curious whether you are already thinking about the next ERC.
Well, I can tell you what the next plans are. I mean, more or less. Okay.
Already submitted.
So the idea, I mean, obviously you can, in a sense, understand where I'm going, because I started small, like with words, then moved on to sentences, and now I'm more and more interested in larger and larger texts. So because of course it's hard to create a representation, it's harder and harder to create a representation that is then exploitable or usable for larger textual content. Also, even if not just for technical reasons, like inputting a large text to a transformer is not doable today. And so these are interesting issues, not only at the NLP level, but also at the deep learning and machine learning level. And then you have the issue of what is the semantics of a large text, and how can you transform it into a knowledge base or a knowledge graph. And this is where we're heading. Okay. And this requires other areas like pragmatics, so taking the context into account, not only the context of the word, but the context of the dialogue or the discussion and so on, and implications, implicatures of what is being said, and also common sense. So I need common sense to understand some of what is said, because that is not mentioned in the text, and it's not even mentioned in large amounts of text. So, for example, current language models don't cover all the common sense that we humans have, and this is already demonstrated. And so all of these are interesting directions that are currently investigated, under investigation.
I see. Very, very clear and very interesting. Grazie.
So Roberto,
going up the hierarchy.
Roberto, thank you very much. I have just one concluding question. I want to mention that these seminars are also part of the Italian PhD program on AI. So they are attended by many PhD students. And so some of them are interested in natural language processing. And I would ask to you, on the technical level, is there any further task? So you focused on this free task, but is there any novel emerging task that is worth to be studied by some young student at the beginning of her PhD?
You mean at the beginning, so as a start?
Yeah, to start something and working for a project of 3 years.
So the point is that deep learning invaded the scenario, the area of NLP. So today, without deep learning, I mean, even the ideas that we have are, in a sense, cast into some deep learning approach, because if you want, of course, to get the state of the art. So it's not totally clear how you should answer, because one thing is new areas, new directions, like text comprehension. I think reading comprehension is certainly an interesting direction, or as I said, moving higher up the hierarchy. These are areas that are certainly cool, but there's one thing that I would really like to put forward, that is evaluating the quality of text. And so here we're talking about just areas, and then what a new student should do, maybe approaching this issue from a different perspective, if we're talking about it. But like evaluating the quality of text is very difficult, because even humans, I mean, when we take a translation of a text, how do we know that it's a good translation? It's a difficult issue, right? So can you say, yes, this looks a great translation, but how do you measure it? I mean, how do you say this is better than this other translation. You have a feeling of it, but there's no easy way to quantify this. And this is an interesting challenge. If we're talking about challenges, if we're talking about a student working in a different area and approaching and maybe being interested some way in NLP, maybe multimodality could be a direction, like maybe someone working with vision or related topics and interconnecting with language some way. I think that's the direction that I would certainly see someone doing something else connecting to NLP, or working with knowledge bases, logic, representation of knowledge, finding a way to connect this to language, which has been a historical idea and goal of many researchers, but very hard to achieve.
Yeah. Thank you very much. So I thank you again for this very nice talk and for your time in these questions. So
thanks again for the invitation.
It was a pleasure to have you here. And so to all the community, I recall that we have our next seminar in December with Francesca Rossi. So thank you very much and see you for the next seminar.
Thanks a lot. Ciao, bye-bye.
Bye.
Ciao, grazie.